Nope, we just have the lab final at the end. So next week is our lab final and checkout.
Okay, so next week is the last week,
Yeah,
so there's nothing the week of the 9th, right?
correct. Yeah, that's week 11.
I had it written down that we had a lab that week.
Yeah.
That feels wrong.
showing. All right, let's get started. So happy Monday. I did not post a link yet. I should still do that. But did people catch the guest speaker on Friday? I don't know if people got a chance to do that. It's just on my YouTube page. So I'd mentioned there was an extra credit opportunity. Oh, hang on. Sorry, give me a second. It's mapping. My pen's mapping wrong. There we go. All right, so I had mentioned that there was a small extra credit opportunity, if I could spell. So 5+ points on your final, and the deal was that you just had to watch this guy. So I'll post a link, but basically the video is on my YouTube channel, so y'all should be able to find it. So video on YouTube. And so it's a doctor, I forgot his name, I think it's Dr. Richardson. But basically, I mean, you should be able to find it. He's an eye doctor, and you just have to watch like probably about the first hour, because he went on for a while like answering questions for an additional hour, and the audio gets kind of fuzzy at that point. But yeah, if you just watch, the main point, and then just send me 1 or 2 sentences of what was cool, what you learned. I'm not looking for a huge essay. I just want to know that you watched it. So that's on the YouTube. I'll try to post a link, during class of the direct links in case you can't find it, but it should just be there on my page. And then I'm just catching up on grading. I think I neglected a few people's things, but I'll hand back what I did grade. And then, yeah, last lab this week, so we do have the lab final next week. So we should at least talk about that briefly. So there'll be a lab final, so you might be expected to do like a small manipulation or calculation. So probably, if anything, like a density or mass, or maybe like a length measurement, just something simple. Yeah.
Will it be like open notes?
Yeah, so it'll still be open notes, and then I might ask like some questions about certain labs or like where you need the lab. So one example could be like I might ask a question about pH or indicators, so that's going to be from today's lab. So like, oh, what color would you expect this to be? Or like, what pH is shown in blah, right? If all these indicators are this color, what do you think the pH is? So something maybe about that, or other, lab-related questions, again, where you could reference your notes. So I might ask easy stuff like, the flame tests, just kind of some obvious ones, just kind of recapping the lab, or other small like calculations from lab. So I'll just say small calculations, similar to lab. So, right, like maybe finding the moles of something, I could, kind of give you data for that, and then you would have to calculate the moles and formula. That's kind of the idea. But I plan to make it, relatively short and easy for this class. And then in addition to the final, that's when we'll do the checkout. And so that will also be a small portion. So just cleaning out your drawer, cleaning your glassware, at least reasonably, you don't have to sit there and scrub every piece, but making sure there's no egregious things on there. So checkout plus cleaning, so that'll be part of your grade, and get everything squared away. So try not to miss it, because you don't want to miss it, the cleaning part, because then it's hard to make up credit for that. So be there. So that's next week. And then that means week 11, you have nothing but the finals. Yeah.
So either, will it be next Monday or next Wednesday?
Whichever your lab section is.
Okay.
Yeah. Any other questions? And like we said, right, we killed that lab 8. We accidentally forgot about that. But yeah, so no lab 8. And then I'll probably still drop like another lab grade and probably like a quiz and a homework grade. So just looking towards your future grades, which I'm going to have to do manually anyways, because your Blackboard is insanely messed up. But that's another story. Any other questions, comments?
And is it the final, like chapter 1 to 9?
Oh, so our final, so the lab final could be anything, right? But then our final, which I'll need to post some more information about that. But in general, so I'll just call final. So we'll just be focused on the latter chapters.
5 through.
Yeah.
Okay.
So it'll be 5 through 9. But again, right, chemistry is cumulative by nature. So that is the only problem.
Meaning like we'll be using stuff from like earlier.
Yeah, so you might still have to name stuff. I think the naming is the biggest thing. Like, I don't think I'm going to test you explicitly on naming, but right, you might still have to name stuff so you can write equations and stuff like that.
Phosphate.
Yeah, so right, like it might say iron 3 phosphate, reacts with sodium whatever, and blah, blah, blah. But we'll do a review for the final, so that's the plan.
Will there also be a lab final review or no lab final review for that?
Like a review for the lab final?
Yeah.
No, I wasn't planning on it because I'm planning on making it hopefully easy enough. But.
Will it be like 13 questions again?
The final? Probably something like that. That seemed like it was an okay test for this class. I have to see what my current iteration is and how much I want to modify it. All right, other questions, comments? We almost to the end. All right, so now let's do chapter 8, which ties in well with our lab. And okay, so now we're just kind of revisiting, well, what is a solution? And so of course we can observe this. So we can have table salt, of course, mixed in water, right? And it appears to disappear. But we know that we're making, right, a homogeneous mixture. So we've kind of mentioned homogeneous mixtures before. And, right, obviously the salt is there. You could taste it, or we could, of course, use a physical change to re-separate them, such as boiling. And so now we can start defining our solution in a little bit more detail. So again, right, these homogeneous mixtures are called solutions. We've dealt with plenty of them in lab, from, right, our base solutions, of different molarities. We've worked with copper chloride, sodium chloride, all these things, right, in different solutions. So basically anything can become a solution. And so then we can say, okay, the minor component, so what's being dissolved, is called the solute. So we'll say what is dissolved. And then in our case, so what we've seen in lab, right, with our sodium hydroxide or all our metal solutions, is they're all dissolved in water. In our case, right, that's what makes them aqueous solutions. And so then we can say that for these aqueous solutions, right, our solvent is water. And so that's the major component of all those little dropper bottles, right? They're all just something dissolved in water. And so you've worked with, again, a ton of those today. Or not just today, but our whole quarter. And I'll throw in there, so check out phenolphthalein. So phenolphthalein is dissolved in ethanol. So just a different solvent solution. So just something to keep in mind, again, as we talk about like dissolves like. So phenolphthalein is an organic, so that's why it's dissolved in an organic solution, or I think it's like, I can't remember if it's cut. I want to say it's 95% ethanol, but I have to check the bottle again. But either way, right, whatever your solvent is, so that's the major component. And so then let's talk about other mixtures. So then we have what's called a colloidal mixture. And colloidal just refers to the size of the particles. And so they have to be large enough to scatter light. So these are usually like on the nanoparticle scale. And so this can make mixtures appear kind of cloudy or opaque. And we have this phenomenon called the Tyndall effect. But let's talk about this because you know what this is without realizing it. And so let's look at this first example here of the Tyndall effect of a colloidal mixture. And so we could have a gas and liquid dispersion, like a liquid aerosol. And so you can see this with like fog, right? And so fog, the whole point of the Tyndall effect is that, again, right, it's scattering the light. And you can think about that with fog, right? So if it's a foggy day, right, it starts bouncing the light off in different directions since the little, particles of water scatter it. So there's one example. Same thing with, so you can have a gas-solid dispersion. And again, you'll get the Tyndall effect. And so I often think about, like, have you ever tried to, you're like banging out your couch cushions or whatever, and then a cloud of dust goes in the air, and then the light's coming in the window, and then you see like your dust kind of shining off the light. Or maybe like smoke, if y'all are smokers, like you blow your smoke. Huh? Well, rainbows don't have the same scattering effect, so that's different, right? That's light just being split. But we're talking about like a physical particle that's disrupting the light. So that's why I brought up, smoke. So again, same thing, right? You blow your smoke out into the light, and it looks cool because it's reflecting everything. And so those are kind of the more obvious Tyndall effects. And then just looking at other dispersions, so you can have whipped cream and shaving cream. So those are also colloidal mixtures. Paints are mixtures, so again, right, they're colored by something that's a certain size. And then obviously gold in water or other pigments, inks, so all those can have the Tyndall effect. Again, right, it has to do with particle size. And then we can have other mixtures, so a solid gas mixture like the pumice stone, so obviously it has little holes left over. Or, Jell-O and cheese can have the same effect. And then you can have solid-solid mixtures, such as your gemstones, and then, right, the impurities give the color.
Back to the
Oh, that's cool. Yeah, you should send me a link of that. So in case you didn't hear, she was just saying that an artist was like using different lights and clouds to make mixtures. So yeah, once you send me that, I'll probably share it because that could be cool. So yeah, mixing art and chemistry. And that's something to, think about too, like how they make paints and everything, right? It's a chemical, you gotta have a chemical and mix it with stuff. And that goes into formulations too. I once knew a guy too who literally, like, his job was to watch paint dry. So, whatever that tells you about formulation chemists. But yeah, he had to watch it dry and, compare the different formulas. So, anyways. And so now let's start looking into, again, kind of how we make these solutions. And so again, we'll talk about salt and sugar. And so kind of what happens when you dissolve these two? Which one's more soluble? Just what you think. Yeah, the salt one, right? So the salt one should be more soluble. And so why is that, right? It has this like dissolves like here, but before we scroll down, kind of what are we thinking? And then what's sugar? What's the distinction? Kind of what happens when you dissolve sugar? And you could even think back, right, because I brought the little water molecules in so I could go get them again, the little magnets that we looked at last week, because that's that same sort of idea. So what's just the basic difference between salt and sugar? So which one has hydrogen bonds, though? Well, water has hydrogen bonds, but then what about salt and sugar? We have water. Thinking about that. So, I mean, they both kind of dissolve, right, to some extent, but we're still trying to tease out, well, why is salt more soluble than sugar? Sweet. And so think simply, though, because no one's even answered the simple question of, right, what's the basic difference between salt and sugar? What type of compound is salt? Ionic, right? So that's half of it. So we have ionic versus a covalent compound, right? So again, maybe I should go grab those magnets, but think about how the magnets surrounded each, right, either cation or anion. So that's part of why salt dissolves so readily. And again, I can grab them if people want to see them again. But you have to think about how the little oxygen of the water, right, especially from all our magnets attached and surrounded our sodium, right? So that's how it's dissolved, is that it's literally surrounding and encapsulating our sodium, right? Because again, it's ionic, so they're already separated, our sodium and our chloride. So there's only the electrostatic forces holding them together, so that's why water can come and disrupt it. And so somebody did mention, right, hydrogen bonding. So, okay, we mentioned that water had hydrogen bonding. And let's look at sugar. So I pulled up, or if I can, sorry. So I pulled up just fructose out just so we can look at it. We could also look at glucose. They're all pretty similar. What do we notice at least? What do you notice about the structure of it?
Well, it's balanced, but like,
Well, like, look at the groups, though. What do we say about those? Yeah, hydroxides. So then if we have hydroxides, what kind of intermolecular forces do we have with the sugar, at least? So not combustion, but can you remember the intermolecular forces we talked about last week? Because it's kind of building on this, at least with the like dissolves like concept. And we had kind of touched on it last week as well, but. So it does have dipole, but beyond dipole, what else does it have? So it's polar, but very specific type of scenario. You said it for water. Yeah, so right, we have hydrogen bonding here too, yeah. Gotta think simple, no. But, yeah, so right now we're kind of slowly piecing it together. It's like, okay, well, sugar, it doesn't go in super readily like salt, right? But we still have some hydrogen bonding. Sorry, keep making this larger, bigger. So basically, right, we're just looking for hydrogen attached to oxygen, nitrogen, or fluorine. Okay, we have that. So we can have some hydrogen bonding. So water can kind of surround it, right? But again, it's going to take some work because it's not as simple as, again, the sodium and the chlorine, right, which are really small and can get surrounded and nucleated. And then, right, they summarize this in just like dissolves like, but this is a reference to polarity and the intermolecular forces. And I think we had briefly talked about it the last time, but that's why we were talking about like, oh, hexane dissolves like fats or other oils, right, that those would be used to clean up oil spills since those were both nonpolar. And we can look at that again, right, as a refresher. So if we compare, and again, I said you shouldn't use hexanes because they're toxic, but let's pick pentane then. So, right, we're looking at these straight chain alkanes, and then we can look at any fat. So I'm just picking linoleic acid because that's the one that came to my mind. Let me get a better picture. And so again, just appreciating like dissolves like. So even though this linoleic acid has one hydrogen bond over here, right, we could argue it's a little polar. But the main structure of this linoleic acid is nonpolar, right? So then we're saying, okay, like dissolves like, so nonpolar is dissolved in nonpolar. And so like we're seeing over here with this example, we have our ionic compound, right, goes readily into water. And sugar, when we said, you know, we do have to kind of work it in a little, but it still goes in. You know, has enough hydrogen bonding, enough polarity to still get in there. And so then, again, thinking about at a molecular level what happens, and again, we can get the water cups if that is helpful. And so basically, right, we have what's called our solute-solute interactions. So these are just between our molecules. Right, so again, going back to those electrostatic forces that are holding them together for our ionic compounds or whatever attractive forces. And then, right, there's also attractive forces between our solvent-solute, so trying to disrupt that. And so basically, right, if your solvent-solute interactions are stronger than your solute-solute, then they dissolve. And so we see that. And let's see, blah, blah, blah. I was just trying to see, I was looking for a certain chart. Okay, maybe I don't have it. Oh, this is what I was looking for. So we talk about it later, but I just wanted to point this out. This is also kind of where solubility rules come into play. Because again, right, we're just kind of making our best assumptions, but this is where you have your solubility rules, right? There might be exceptions because it's sometimes hard to predict, right, what's stronger, the solute or solvent solute, and that also accounts for strange discrepancies. So we'll revisit this, but so again, we'll say refer to solubility rules, and I'll emphasize, right, sometimes you just have to do it experimentally, right, see how much you can get in. You can obviously make predictions, but have to test it. All right, so I feel like we've seen this a while, and so we'll see it again. So again, right, emphasizing our uneven distribution of electrons in water. So again, really emphasizing the polar nature of water. And I'll just point out again our partial negative region on our oxygen, and then our partial positives on each hydrogen. So again, right, that's telling you how it's going to dissolve your ionic compounds and which side it's going to be oriented towards. And so like we saw with our little magnets, again, the positive cation is attracted to our negative electron density on our oxygen, and then our chlorine was attracted to the positive electron density. And again, we can bring out the magnets, we can see how we can surround it and nucleate it. And, right, so just recap, sodium chloride, ionic compound, metal plus a nonmetal, and then obviously these ionic compounds in water are salt solutions. And again, right, that's what we've seen in lab, that's what we've worked with. And then just another depiction, again, just showing everything nucleated now fully. Again, just kind of how we were seeing in our magnets. And then just kind of putting the pieces together. So y'all did this in lab, right? So now we can think back to the lab that we did with our little light bulbs. So if you remember, you had a beaker of just solid sodium chloride, and right, the light bulb did not turn on, so no light. And then you put it in some water, so just plain water, and there should have been, right, essentially no light. But then the key was, okay, well now if we combine the two, so H2O, and then, right, we have our ions dissolved, so now these are floating around, and they have motion. And so because our solvent gives it motion and they're free to move around, right, that was able to light up the light bulb. And so this would also be, right, concentration dependent. Maybe I'll bring the light bulb in on Wednesday, and we can look at some more things light up. And so then, right, we get to these terms. And so again, just kind of recapping. So then we said, okay, an electrolyte solution is basically anything that will conduct electricity. So that's an electrolyte. And then non-electrolytes obviously do not. So that would be sugar. And so sugar, right, even though you can get it dissolved, it doesn't form any ions. So that's our key. So no ions in solution. And then anything that's a non-electrolyte should also be a covalent compound. So that will help you distinguish. And then obviously electrolytes should be ionic, at least for the most part. I'll mention, so this is where we're headed with this. So we'll say weak acids and bases, though, will be electrolytes. So we'll look at that, like I said, probably in a demo, and then we'll keep talking about that into next week. And so again, this is a nice little graph to just kind of go over what y'all had reasoned out, right? So you all have eventually determined that, okay, we had an ionic compound. And again, right, this is just emphasizing that they can fully disassociate, right? They're fully surrounded. And then again, comparing that to the sugar, so we just have, right, these hydrogen bonding interactions. And so that helps dissolve it, right? But again, there's nothing getting protonated, deprotonated. And you can kind of see, I know these, they get kind of hard to tell what's going on, but just kind of imagine, again, right, the water, hydrogen bonding, and helping to dissolve it. So does that kind of make sense? The distinctions too. Because again, even though it's dissolved, our sugar, it's still a non-electrolyte since there's no discrete charges. All right, so then this is just further defining what an electrolyte solution is. And so it says that strong electrolytes completely disassociate. And so this is typically, again, your ionic compounds, but I'm going to add to this strong acids and bases. And so again, we're kind of like dancing around this subject. You kind of got a taste of it today with the pH measurements, or you'll play with it on Wednesday if you haven't had lab. That's part of it. So again, if something has a strong acid, it has nothing to do with how dangerous it is, but rather just does it fully associate. And so we can say, well, HCl is the same thing, so it's a strong acid, again, fully disassociates. And then on this calcium chloride, just note, right, there are 2 chlorines in there, so then 2 equivalents of chloride. And so like I mentioned, our weak electrolytes, the only real example I can think of are organic compounds. So weak acids and bases. So there they have formate, but I would also put under here, right, acetic acid and acetate. Well, that's confusing. Maybe I should rewrite it. Let me rewrite. I don't want to confuse people. So that's formate, but I just like talking about acetic acid since obviously we did a titration this week, or will do a titration, plus it's also vinegar. So, yeah. So non-electrolytes do not disassociate. So like sugar, so they can't do any of this associating. And so part of why they disassociate, so now I'm drawing acetic acid. So this is actually acetic acid. And I don't like their arrows here, so they should be equilibrium arrows, so little half arrows. And basically the key, so we haven't quite gotten there, but we're getting there with acids and bases, is that it has to have what's called an acidic proton, and basically that proton can come on and off. So now we have acetate, so the conjugate base, which we'll get into, and then H+. So again, right, our weak acid, so it's weak because of this partial dissociation, right? And this should remind you of kind of equilibrium, right? So there's some sort of equilibrium where it can go back and forth, right? Some of it is associated and still together, and some of it is not. And I'll add one more. So another classic example is HF, and I like talking about HF because obviously HF is pretty dangerous. HF is one of the few chemicals I would probably put on my list of things I would not want to work with. I work with pretty much anything. But HF, why it's so dangerous is because apparently you don't really feel it if you like get it on you. But the problem with HF is, right, then it'll go into your bone, and then it has the potential to dissolve the calcium in your bone. And then the problem with that is that the calcium could then re-solidify, right, somewhere in your bloodstream. So then it's just, you know, a game of roulette of where it re-solidifies. So obviously if it's, you know, somewhere in your brain or your heart, that could cause major issues. But
Basically, it has the potential to cause an embolism.
yeah, or some sort of, yeah, heart attack, blockage, yeah, brain aneurysm. So that's why if you're working with HF, there's like a special calcium-based paste that if you get some on there, then you put that paste on there so it neutralizes the HF. But yeah, HF though, super dangerous, but a weak acid because of its tenant, again, it doesn't fully disassociate. So dangerous. And then obviously, right, you see in the movies, they always use it to dissolve people's bodies. And anyways, pretty nasty. And HF also etches glass and stuff, so it has to be kept in plastic. But weak acid. And so again, this is just emphasizing, so basically all your ionic substances, at least, right, are basic ones that are soluble. So again, right, these are going to be soluble based off of your solubility rules. So these are going to completely disassociate. So again, sodium chloride. I'll add in there, right, sodium hydroxide. So that's a base and a strong base. Again, since it fully disassociates. And so then just going through, again, our acetic acid is weak since it partially disassociates. And so this is a good reminder. So again, most molecular compounds are just intact. So it's just those acids and bases that tend to disassociate. And like we mentioned, that's why that's a non-electrolyte solution. So just to emphasize, and that's why I want to bring in the light bulb for you on Wednesday. So acetic acid does turn on the light bulb, but it will do it weakly. So we'll compare that, right? So we look at same concentration of acid versus same concentration of acetic acid. We'll see that the light bulb is weaker. So like I said, I'll bring that in on Wednesday for us to kind of play with a little. And so here's a good picture of what I want to show y'all, but more exciting if we do it in person. So like we saw, you know, we can do this again with a non-electrolyte solution with sugar, see that it doesn't dissolve. I'll bring in the acetic acid. We'll see that it weakly turns it on, and then we compare it to either the strong acid or we can compare salt again, and we'll see the difference. So that's all that is emphasizing. And so again, right, I think did I give y'all solubility rules? Oh, I did not. Sorry, I was thinking of my other class. I will print out solubility rules for y'all. But basically, we need solubility rules because there's this caveat of not all ionic compounds dissolve in water. So one of those is silver chloride, for instance. But everything will make more sense once you have these solubility rules. So I'll print these for you so you have a copy during our break. But essentially, you can kind of look through these rules. And you might start to recognize, again, some things since we've worked with a lot of compounds in lab. And so we look at, so generally our group 1 are soluble, so lithium, sodium, potassium, and ammonium. So these are always all soluble. And you can think back, like we probably have worked with, some lithium chloride in our flame test, and you can remember, right, that just was a clear liquid in a bottle. Same thing with sodium chloride, potassium chloride. And then next mentions, okay, well, nitrates and acetates, those are usually all soluble. And again, right, I'm sure we've worked with a lot of nitrates in here. And then now we can start to look at our exceptions. So our halogens, we have chloride, bromide, and iodide. So most of these are soluble unless they're paired with silver, mercury, or lead. So those tend to be the heavy metals, and those tend to be insoluble. And again, right, this goes back to just those solute-solute and solute-solvent interactions. But right, again, we can't predict it, so that's where solubility rules is keys. And then same thing with sulfate. So most of these are soluble. And then these get weird too, because sometimes even different charts will say different things. And so, as a reminder, let's see, where the heck did all this come from anyways? And so the solubility rules, like I mentioned, it has to be determined experimentally. And so you can kind of get an idea of what is insoluble. So right, it mentioned that calcium sulfate tends to be insoluble, or at least right on that line. And so if we look at Wikipedia, it tells us more specific data. So calcium sulfate is 0.26 grams in 100 milliliters, and it tells you the temperature. And so yeah, that's fairly insoluble. There are obviously things that are more insoluble. You can get some in there. And this is also just to say, like, this is where you can take it deeper. So if you take the 200 level class in this, then you can start to quantify it and do math with the KSP. But all I'm trying to show you is this is where these magical rules came from, right? They're based off of experiments that people ran, and then, you can have slight discrepancies, again, based off of those results. And then, so looking at the rest of the rules, so hydroxide and sulfides are generally insoluble now. And notice, right, just the exceptions when it's paired with group 1. And then these could also be right on the edge. Same with like calcium hydroxide, barium hydroxide, right? These are all slightly soluble. So sometimes they do act as a precipitate in your reactions. And so same thing with carbonates and phosphates. If you vaguely remember from that unknown identification lab, you use a lot of carbonates and phosphates, right, to detect for calcium presence. And so a lot of those compounds are insoluble, again, with the exceptions mainly being group 1. All right, so then we have to look at our solubility rules. And so going back over here, so right now we're saying, okay, silver nitrate, we had mentioned that our nitrates were generally soluble, so we expect this to be electrolyte, versus, okay, now we can look at silver chloride, and then, silver was one of those exceptions, so this would be insoluble. All right, let's see if we can do this little practice. I just want to copy it again so you can see both the problem and the rules, because that would be helpful. All right, so try those. So lead chloride, copper chloride, calcium nitrate, and barium sulfate. So just try to read those solubility rules and determine soluble and insoluble. Then we'll go over them. All right, let's go over them. So what do we think for lead chloride? Soluble, insoluble? So insoluble, that's what I heard. Everybody get that? And then, what about copper chloride? Yep, so soluble. And again, probably I've worked with that one in lab. What about calcium nitrate? So that's another soluble one. And then barium sulfate? Insoluble, excellent. So yeah, pretty easy once you have the rules. So I think this is a good place for a break time. Although I did want to show you, so Madison had mentioned that there's an artist that does these cloud pictures, and they are pretty crazy. So somehow they control the temperature, humidity, and lighting, and then take these pictures of these clouds. So that's pretty crazy. So it's kind of cool to look at. So I'll put that up there. I don't know if people want a link to it. At least.
Bragging everyone, I just created my own weather. Deal with that.
It's pretty cool, like creating a cloud. So there's also just another gallery. So I'll just leave that up for people to appreciate, and then we can go ahead and take our 10-minute break. I like the comments in the chat. Somebody said he must be a Harry Potter fan.
You know how people say, what's the weather like up there or down there? Well, what's the weather like right here?
Yeah. Cloudy, the chance of cloud.
I saw it and I was like, I bet he used like to me too.
Yeah, I'm really curious how he did it, honestly. All right, let me try to print y'all some solubility rules. All right, I think we're missing this one person, tubulol. So everybody got solubility rules, and if you're online, you can just look at any solubility rules. They should all have the same information. Yeah, I think I passed out solubility rules, but if I skipped anybody accidentally. What'd you lose?
Pencil.
I have an extra one here.
All I did was I walked down the hall and now it's good.
All right, so as we get back from break, right, so we're looking at this chart that we kind of mentioned. And so again, just kind of in general, our solubility is generally given in grams of solute that will dissolve in 100 grams of water. That's a super general statement, right? So as you saw on Wikipedia, there's going to be all sorts of different measurements and different units of water. I don't know why they're not more consistent. And then for most solids, right, the solubility increases as the temperature increases. And so that makes sense, right? We can think back to even our gas chapter. So we're saying, okay, kinetic energy is related to temperature. So that makes sense, right? Greater kinetic energy, they should be moving more and dissolve more. And again, right, with that one notable exception being this cerium sulfate. So I don't have an exact explanation for that. We'd probably have to go look up like a paper that's about this topic and figure out exactly what it is that's about, you know, the cerium sulfate interaction that makes it stronger as it gets heated compared to the water cerium sulfate interaction. So, you know, again, really the important thing to note is that, again, temperature increases, so does solubility for the most part, with very, very few exceptions. And so, of course, you could also use these solubility curves to predict whether, you know, a particular amount of solute would be dissolved. And so if it was saturated, it would be right on the lines that would basically be kind of the limit of what can be dissolved when it's saturated. Unsaturated is anything kind of below the line, so that's saying that you can get more in. And then a supersaturated solution is usually some sort of special forcing conditions, you know, typically like heating to get a more concentrated solution. And so probably a good example of this would be like, you know, getting a supersaturated solution of sugar, and you could probably get it nice and hot and boiling and get more dissolved and make, right, a simple syrup of it than is normally dissolved, right, than if you just take, you know, plain sugar and try to stir it around in water for a while compared to, again, making a simple syrup. And so supersaturated, again, generally you have to heat it or some sort of weird conditions, or it could be temperature pressure. And so now let's look at gases. And so I'm just going to put a big star in that gases are essentially the opposite of solids. And so let's look at what we mean by that. And so first of all, right, they have just a lower solubility already to begin with, since we're trying to do a gas in a polar solution, right? And then obviously these gases tend to be nonpolar, right? Even CO2 is nonpolar. And usually if you have a gas with a high solubility, it's actually reacting with water. And so again, we find the opposite for gases the solubility of gases decreases as the temperature increases, right? So that kind of makes sense. So if it's getting too hot, then your gas is just bubbling out of solution. And here's a little example of this visually. And then I always say, though, it kind of depends how you like your soda, though, right? So if you take your cold soda out of your fridge and then you pour it out, so these should also be new bottles, then the cold one is not going to fizz a lot. But if you do, a room temperature or warm soda and then you pour it out, right, it's a lot fizzier.
I hear if you turn like the cup to the side, it should reduce the bubbles.
Yeah, that could help too. But right, what we're trying to see is basically, right, that the cold one has less bubbling than the warm one, right? So because of that gas being released. So probably if you put it to the side, that kind of helps not have so much turbulence where you're essentially, right, releasing all those gases. And so this also mentions that the change in enthalpy of this is exothermic, since, right, we're not overcoming solute-solute interactions, since, again, right, it's a gas. So it's already nonpolar, so that, right, there's really no solute-solute interactions to overcome, right? Because think about what that's saying. That's saying, right, your thing that's dissolved, like, what's that interaction? But then what do we know about gases, right? They're already nonpolar. They already have pretty weak intermolecular forces, right? So they just take off and bust out of your soda solution. And then, so how do we vary this? How do we get more dissolved? And so then now we're getting into how can we make it saturated or supersaturated. And so as we mentioned, we can make a saturated or supersaturated solution by generally changing the temperature, but sometimes the pressure as well, and then again allowing the system to slowly go back. So again, I'm thinking of our simple syrup, right, our sugar. And so some solutes, instead of coming out of solution, just get stuck, and then we get this supersaturated solution. So again, our liquid simple syrup versus, so sometimes, right, if you take your sugar and make a supersaturated solution, you can make rock candy, right? So that's kind of a difference. And so basically, right, our simple syrup is our supersaturated solution just staying in place. But then, right, we could also take that supersaturated solution, and especially if you give it somewhere to nucleate, that makes rock candy. So then, right, it's going to drop out of that supersaturated solution and instead crystallize. And so again, supersaturated solutions can become unstable and lose all their solute when they're disturbed. And so you can obviously shake a carbonated beverage, and then that will disturb it, and it will explode out. Yeah?
Your battery is about to die.
No, thanks. Well, okay. This charger is really finicky. And so sometimes you see like cool YouTube videos. I have to find like a good example of this where people take like a boiling pot of water and then they take it outside in the cold, and then right, it instantly goes to snow. So that's kind of the same idea of these supersaturated solutions and manipulating them. But I'll try to pull up some videos of this for later. And this also, didn't someone ask me about Mentos before in here? And diet soda? I thought someone had brought it up. But this starts to go into the Mentos diet soda thing. So why Mentos causes the diet soda to explode. So same sort of thing. Basically, the Mentos especially with the diet sodas, something about that artificial sugar. It starts like nucleating more on the Mentos, and basically that disrupts, right, the carbonation, and next thing you know, it's spewing out. And it's not any chemical reaction, it just has to do with this solution being disturbed and the Mentos providing some sort of surface to nucleate onto. And so that's where you get the exploding from. And so then we can ask, well, how do we can stuff then, essentially? And I forgot when canning was developed. I think it was like the early 1900s when they started making soda and then wanted to figure out, well, how do you bottle this soda? Because that was pretty cool, making soda. And so we have this relationship here. And so it's pretty straightforward. We just kind of have to piece together what the different things are. And so we have this KH, and this is called Henry's Law constant. And so, right, you would obviously have to be provided this, or you look it up. And so every gas has this Henry's Law constant. And then what's nice about this constant is it walks you through the math, right? So we're saying that for CO2, our KH at 25 degrees Celsius is 3.4 times 10 to the negative 2, and now we're giving a concentration of molarity, right, per ATM. So this is obviously, right, concentration related to a pressure. And so now you're imagining, well, this is how they can figure out what pressure to can these under. So obviously, right, they're canned under some sort of pressure to get that CO2 dissolved in solution. And then obviously when you pop the top, right, that pressure is being released. And so also why there's arguments for these types of cans, right, with the pop top as opposed to the glass bottle with the thing that seals on there, since that one I think has more of a tendency to leak over time versus these are pretty well sealed. And you beer connoisseurs can probably speak more about that. And again, you can see how the math would go. So notice the solubility is just going to be in molarity, and it's related to the pressure. So whatever solubility you want of your gas, then you just have to get the pressure to that appropriate level. All right, so now let's start to get more into the math of it. And so, again, I think you at least have a vague idea that we have different concentrated solutions, right? Again, we looked at that with our acid. We had 1 molar HCl versus 3 molar HCl. But now we want to understand, well, what does that little m mean that we've been seeing this whole time in lab? And there are also other ways to describe solutions. So obviously we're going to see a lot of molarity. That's a pretty common one used, especially for general chemistry, but there are other amounts. And then you can also have these kind of vague terms of dilute and concentrated. And I would just say dilute is less than 3 molar. Again, very general, rough statement. And concentrated, right, is greater than that. And I just say that for reasons of safety anyways. And what we really care about is the concentration. And again, that tells us how much stuff we have dissolved in our solution. So essentially how to make our solution. So here's a quick just overview of everything we're going to look at. So we'll go over them in more detail. But I'll just kind of point out, so up at the top is molarity. So again, we've seen this. This is a big M that's used in lab. Everything is in molarity. And so that's in moles over liters. And then not to be confused with molality. So the only difference is the R in molarity is an L in little molality. And molality Some people argue it's actually more accurate than molarity, since volume can slightly change with temperature, and so that's why they have it moles per mass of solvent in kilograms, but really less known. And then we've looked at mole fraction, mole percent, part by mass, so all these kind of come back in, and then we'll look at parts per million, parts per billion, and these parts per volume, which you already got a taste for in lab. All right, so here's kind of, right, an overview. And so this is kind of from the perspective of the stockroom here. Because, okay, like how does our stockroom know what to prepare for us, right? That they made us a 0.1 molar solution of sodium hydroxide. And so that's what they have to know, right? They have to know the concentration, and then they figure out the amount. Okay, each student or each group is going to roughly use, so many milliliters for this titration. So this is how many liters we need to make for the class this year. And okay, let's just look at this one. Okay, we want to prepare 500 milliliters of 5 grams in 100 milliliters, right? So then we can see how we're going to have to scale by a factor of 5. And so, right, that's what we want to do, is kind of calculate our mass of solute and then use our conversion factor. And so that's why it's always good to pay attention, right? So sometimes it's a weight per weight solution. So those are just kind of the easiest. If you can just do like percent mass. So 5% by mass is just write 5 grams over 100. And write 100 is always your percentage total. And so let's see how you might physically do this. And so notice that we're using, in this little example, a volumetric flask. And so that would be most appropriate. So these volumetrics are set to measure just one measurement. And so in this case, if we want to make 1 liter of a 1 molar sodium chloride solution, that's why they've selected, right, a 1 liter volumetric. And so now, okay, we want to make 1 molar solution. And so it says, right, 1 molar. So again, that's 1 mole per liter. So that's just the definition of molarity. And so that's what's shown here. So, right, they weighed out 1 mole of sodium chloride, so 58.44 grams. And then the first thing you do is put your solid in, or your solute. Then you want to add water to about here or so and mix it up. And then continue to add water until you reach the 1 liter mark. And you have to do this very carefully and probably adding with a dropper, drop by drop, because of course if you go over this line, right, then your whole solution is ruined and you have to start over again because now it's inaccurate. So you have to get it right at that line, right, the meniscus right there, and then shake it up again, get it all homogeneous, and you have your solution. And usually they have some sort of little cap here, like a ground glass stopper. That's just not depicted in this little picture. So that's how you make your solution. Again, it's kind of roughly. And so now we can look at, again, molarity. And so you probably want to write this one down. So molarity is, again, just defined as moles over liters. And so looking at how to translate that, so if we have a 2 molar sugar solution, then we can say, right, 1 liter of that contains 2 moles, or 2 liters contains 4 moles, or 0.5 liters, right, contain 1 moles. So kind of proportion or dimensional analysis again. Right, so again, big M moles over liters. And so now, if we compare that to molality, so like I mentioned, it is moles over kilogram. And so water does have a density of 1, so that conversion is easy. So H2O, density of 1 gram per milliliter. So that's not going to matter too much for water, but just watch those units on there. Although it would matter, right, for other solvents, so that could get tricky. Then you have to calculate mass based on density. And as I mentioned before, that sometimes this is considered the more accurate way, as it does not vary with temperature, since it's based upon masses. But again, in practice, I never really see molality, at least from my experience. And so write that down, and again, little m, and star that, whatever you need to do, that this is little m molality, so it's moles of solute over kilograms of solvent. And again, note that that's kilograms of solvent. All right, so then we have these different parts. And so that's where you have to be just kind of watchful on the units, because you have to watch whether it's measuring by percent mass or percent volume, or even, right, weight per volume, because you actually had percent weight volume, right? That was from your lab today, actually. So it asks a weight per volume percentage. And so it doesn't really matter, just as long as you're paying attention to what it's specifying. And so usually they're in the same units. So again, ideally, if it's a percent mass, then it doesn't matter as long as you're in kilograms or grams or pounds. And then again, volume, just watch the units, because it could even be, right, pounds per gallon or something weird. So just always watch your units for this one. And just pay attention to what the problem is asking. And so, of course, a percentage is just a part out of 100 parts, so that's what's implied by a percent. So if we have a solution of 0.9% and then notice by mass, so then that's saying we have 0.9 grams of solute for every 100 grams of solution. So again, that's mass, so gram per gram conversion. All right, so now let's look at these parts per million in a little bit more detail. And so our parts per million is described as, right, parts over a million, right? So how many parts we have in a million particles. And so often you see this for like water quality reports, which I'll try to pull up the Medford water quality report while we look at this. And so this is nice, the parts thing, but honestly I get confused by trying to convert parts in a 1 times 10 to the 6 parts. And so I much prefer this way to think about it. And so we can say milligrams, and then that's going to be of solute, right, over kilograms of solution. And then you can see where that 10 to the 6 factor comes out. So right, again, milligrams was 10 to the negative 3, kilograms is 10 to the 3rd. So there's your factor, right, of 10 to the 6 difference. But again, right, if you just treat this in milligrams over kilograms, that will be very helpful for y'all. And so again, right, where I was saying it's out of 1,000,000. And so now if we look at parts per billion, so again, similar sort of concept, right? We have a part out of 1,000,000,000, so 10 to the 9th. But again, this is another one of those that, honestly, that confuses me, trying to think about that. If it works for you, go ahead. But otherwise, I like thinking about it in converting how many micrograms we have per kilogram. And so again, now you see that 10 to the 9th factor. So micrograms, 10 to the -6, kilograms, still 10 to the 3rd. And so there's, again, our 10 to the 9th difference. So that kind of helps. And we can at least look at our Medford water quality report. And so at least, right, appreciate, we have pretty good water here in the Rogue Valley. So that's pretty nice. So, right, we get it straight from the springs and the Rogue River. And then they treat it. And so actually recently, I don't know if you noticed, they actually mention it here, but there was a pH adjustment with sodium hydroxide. So personally, I was kind of curious about that. But part of why you'd want to make your pH a little bit more basic is to hopefully prevent like metals from being stripped off in your pipes, you know, such as copper and any other potentially bad heavy metals. So I assume that was, you know, their logic. I don't know. We should plan a trip to the plant. That would actually be fun. There's just only so many hours in the day. And here we go. Oops, if I could zoom in. And so again, just kind of looking and seeing. So bright barium, so that's going to be a toxic heavy metal. And so it has some sort of allowance. I'm not really sure what this is in. Although I assume this is parts per million for all of these. And so pretty small amount detected, so that seems okay. And then it tells you, yes, it complies. And then cadmium, notice it's measured in parts per billion, so even a lower tolerance. So again, just kind of, and then it does mention, right, corrosion of galvanized pipes is a source for cadmium. So again, that's why I'm thinking they might have decided to make that pH adjustment, but again, I don't know. I wasn't in the room. And just kind of fascinating to kind of look at. So these trihalomethanes are generally considered not that great, and they have them in the parts per billion. And again, you can just kind of compare the max allowed. So right, these look pretty good. Haloacetic acids, again, right, looks pretty good. These are in parts per million now for chlorine. So obviously it's a treatment. But, and then lead, right, measured in parts per billion. And so pretty low, that's good. So that's exciting. Oh, I was hoping for more. I thought there was one where they also had like fluoride. Well, anyways, if you're bored, you can look at the water report, but at least that's why they have those units and kind of appreciate that. All right, so now let's look at mole fraction. And I feel like we've kind of done this maybe inadvertently, but essentially our mole fraction is just our mole of whatever substance we're looking at over the total number of moles, right? So we could kind of think back to Dalton's partial pressure with that. We didn't do too much math examples with that, but same sort of idea, right, with the mole fraction. And as we mentioned for air, right, the total air is at 1 ATM, and then we were able to find, right, the fractions in the partial pressures of each of our substances. And so the mole fraction has no units, and then sometimes you can also be asked for mole percentage. So obviously that's just the mole fraction multiplied by 100. So again, just watch the wording for that. So we'll do some practice with this. But let's look at kind of the other key math part. And it's this equation right here. And so, right, the next question is, and this is also, again, something that the stockroom has to do very often. And so, right, I think I've mentioned, let's just say like our acids, right, they come super concentrated. So usually like 12 molar, or perhaps I think nitric comes in like 16. So super, super, super concentrated, right? But then obviously y'all aren't playing with that high of concentration. And so they have to do what's called a dilution. And so this is the formula you need right here. And I like it in this form too. So this C1V1 equals C2V2. And so what's nice about this formula is that the units don't matter as long as they are the same. So units don't matter, just need to match. So that's convenient, right? So they could be in molarity, molality, percentages, whatever. It doesn't matter. Just you're going to calculate, right, whatever concentration in that unit. And then same thing with the volume, right? They could be liters, it could be milliliters, gallons, whatever. It doesn't matter. You'll just calculate it in the same unit. And so obviously, we're going to notice that these are inversely proportional. And then, I don't know, for some reason, it wants to point out that there's this more specific formula, and sometimes you see it just given as this M1V1 equals M2V2. But obviously, right, that's specific for molarity, and I don't really like that formula because it doesn't matter, right? Again, concentration could be in anything. We've talked about we just finished talking about a billion different units here. So yes, we can use any of those in this C1V1 formula. So yeah, I think it's a little silly that it says that. Anyways, so now let's think about, well, how would the stockroom do this for us? And so this could be a case sometimes, right, where they might have a really concentrated solution of, let's just say, calcium chloride, like this example says. And so we're trying to figure out, well, we need to prepare 3 liters of a 0.5 molar solution, starting with a 10 molar stock solution. And so before we look at like the physical aspect, let's just set up our formula. So C1V1 equals C2V2. Again, the stockroom literally does this almost on a daily basis, certainly a weekly basis, I'm sure. And okay, let's just plug in our variables. So we want 0.5 molar solution, and we need 3 liters of it. So I need to figure out how much volume I need of my original 10 molar solution. So we can just set up our algebra. And let me pull out my calculator. So then we have 0.5 times 3 divided by 10. And so now I need 0.15 liters, because again, right, we're in liters here, so 0.15 liters, or 150 milliliters. All right, and so that's what's shown here now. And so they used a graduated cylinder to just measure out 150 milliliters of our stock solution, and then pour it in to, again, our volumetric. So now this time we're using a 3-liter volumetric flask. And so again, just like before, then I'd probably take it up halfway, shake it, dilute it, then take it up the full way, again, very carefully, and then shake it again to get your homogeneous 0.5 molar calcium chloride solution. And then they just showed the math down here. So of course, getting to our same answer, 0.15 liters. And so again, I'm sure that's how the stockroom made our solutions, right? They have pretty strong, sodium hydroxide solutions, and then they can just dilute it for us. All right, so let's try this practice problem. So what volume should we dilute 0.2 liters of a 15 molar sodium hydroxide solution to obtain a 3 molar solution? So let's see how we did. So I'm seeing us set up, so C1, V1, C2, V2, and, right, so the hardest thing is just figuring out who's who. So V1, C1, and we're trying to do C2, so we need V2. And so now we can plug it in, and again, just double check your units really quick. Molarity, molarity. Okay, liters, we're solving in liters, just to make sure that, right, no one try to do a tricky unit switch on us or anything. And so what do we get for our volume? So y'all can yell at me while I punch it in.
Just got flat one.
So 1, yep, so we all got 1. So we need a 1 liter solution. questions on that one? Okay, hopefully it feels not too bad. All right, so last concepts, we'll see if we can finish before class. And then that will leave Wednesday for just doing practice problems, but we'll see. And so now let's look at freezing point depression. And so it's saying that the freezing point of a solution is lower than the freezing point of a pure solvent. And well, this is really relevant right now, and we can think about it. Well, we haven't quite started icing or putting salt on the roads. But right, we can think about, oh yeah, this is true, right? Well, why do they salt the roads, right? It's because of this phenomenon. Or really, they put rocks here, which is, I'm much happier about environmentally. So, right, the problem with salt and why I don't really like salt is, well, not only does it get on your car, right, and cause rust, but we're here in the beautiful Rogue Valley where there's rivers everywhere, and so I believe they don't use salt here because that salt, right, is just going to end up in your freshwater system. So you really don't want that. And so I think it's great that here they use rocks. But again, right, same sort of idea. You're making a solution. Obviously, those rocks aren't going to dissolve quite as well as the salt, but again, from the environmental standpoint, rocks are way better. And so again, the point is now we have a solution, and so those rocks and the salt disrupts the intermolecular forces of the water, right, trying to freeze. And so that's why it lowers the freezing point and then, right, melts the ice so y'all can drive on it. And so again, as long as you can remember this big freezing point depression, that's all you need to remember. Freezing point depression. Freezing point is lowered in a solution. And then, again, the math part, I don't want people to get overwhelmed. It's just something that I would have to provide on an exam so we can see the difference in our freezing temperature is related to our freezing point depression constant. So you'd have to be provided this KF, and then again, right, let your KF dictate your math. So it's in degrees Celsius per, now this is the only thing, look at that unit, it's molality. That is the only strange thing in these problems, is that these KFs have a molality value. But you can see, right, it's just basically proportional to the concentration. But we'll practice some math problems. And then I also like this graph. Again, this graph is nice and it helps you. So right, blue is our pure solvent, and what we're appreciating is, again, this liquid solid line. And okay, freezing point depression, right, again, that line is lowered as we go to a solution. And so this is, right, your phase change from solid to liquid. So again, just appreciating how it's lower. And so like we just talked about, so right, pure water freezes at 0, and then adding salt disrupts this equilibrium. You know, you can also think about like your popsicles. Sometimes they're a little bit harder to freeze than just pure ice, right? Because they got sugar and juice and whatever else in them. Or, you know, if you like alcoholic ones, that's even more difficult to freeze with ethanol. And so again, right, to return to equilibrium, we have to have a slower temperature to get that ice, in this case, to crystallize out essentially. And so again, you'd have to be given a chart like this on an exam to help you with the problem. So you have your normal freezing point, so AKA just a pure solution. Obviously water is at 0. And then we have our KF, so again, that's for freezing. And then let's take a look at KB real quick, because we have KB here. Well, that's going to be for boiling, obviously. But let's read about that. So we'll go back to this problem. In fact, we may revisit the problem on Wednesday. And so the other key point, again, start, you had freezing point depression, now you have boiling point elevation, right? So they're opposite. And so now the boiling point of a solution is higher than the boiling point of a pure solvent. And so it makes the comment for a non-volatile solute, so AKA like just a normal, right, ionic or covalent solid. So what it's referring to would be like another liquid, right? Like if you had a liquid-liquid mixture, then that's a different story. But if we're just talking about non-volatile, aka we put some solids in there, and this goes into the great pasta debate, we'll call it. But basically, there's always a debate about pasta, right? Should you put the salt in before you boil the water? Well, technically that water has to go slightly higher. So now you maybe taking longer to cook, but then if the water is slightly higher, then theoretically it should also take your pasta less long to cook. Anyways, I don't know if it makes that much of a difference. But that is a great pasta debate for those of you that are pasta experts. And so similarly, right, again, it's based off of that KB factor. So it, again, you'll have to be provided the KB with whatever solvent, and the units are, again, degrees Celsius per molality again. So again, just make a note that that's molality. And so again, you'll get your difference in temperature where the solution is higher. Okay, let's maybe try this one. I know we're running out of time. So see if we can figure out this one. What is the freezing point of a 1.7 molal, and then watch the wording, aqueous ethylene glycol solution. So just so y'all can see this one, again, I know we're kind of running out of time. And so again, right, our change in temperature is essentially equal to, right, our KF times our molality. And then everybody has gotten tripped up previously because they were trying to find like ethylene glycol on here. But, right, the keyword is aqueous, so we're starting with a water solution, and we added ethylene glycol to it. So we have to start with our freezing point of water and using our KF. So then that turns into 1.86 times 1.7. And so then we get a difference of 3. So then obviously 0 minus 3 for our normal, gives us, right, our new freezing point of negative 3.2. And so we'll pick up with this on Wednesday, so we'll do another practice with the boiling point. But again, right, I'm trying to make you feel comfortable, use your dimensional analysis, it should be pretty straightforward. Like I said, I just have to give you all this data and the constants. All right, we're probably out of time, so we'll stop there, pick up some more examples on Wednesday, and finish the last little bit.
Multiply the 1.86 times the 1.7.
Yeah,
What
so,
did you do after that?
oh, and then you just subtract it from the normal boiling point.
Oh, okay.
So water, it's just 0 minus that, and then if it had been anything else, you know, like ethanol, then you subtract it. But
Because it's an aqueous.
yeah, but because it was aqueous, we did the water boiling point.
Here's that lab 6.
Oh, thank you.
Are there any meetings you need to attend to either today or Wednesday?
No, so I'm free. So yeah, I can stay after today, or if you want to wait till Wednesday to chat. Either way or both.
I just need to catch up on last week's homework.
Yeah, so if you want me to hang out while you do
I need
homework?
just a bit.
Oh, yeah, yeah, of course.
I know I'm missing quizzes now.
Yes, I
can't
know you
remember
were,
which ones it is. I think it's quiz 5 and maybe quiz 6.
you might just be missing that one, because the week before, we didn't have a quiz. So that was last week's quiz.
Okay, and then there's this week's quiz,
Yeah,
which I will be here for.
okay. And then, Maren, are you missing last week's quiz?
Yes.
So if you want to take that,
Yeah, I can take